Thanks, Matt. So this last talk of the day, I think it's one of my more fun talks. Hopefully it'll be a little bit entertaining. So I'm going to talk about a very small, apparently modest field program that we did just before COVID at Siple Field Camp. And there were only 4 of us, myself, a graduate student Madison Giz, and then 2 Antarctic support contract folks, the camp manager Jen Dennis and camp engineer Kyler Hale. They were among the, they were the best of the best in terms of support. So a small field program that worked out very well. Its predecessor was something much larger. Some of you were here in the previous session, and I introduced AWARE, so I won't talk about AWARE too much. It was one of the biggest things climate science-wise in the Antarctic. We deployed the ARM mobile facility for a year at McMurdo, and we also got to Waste Divide Ice Camp with some surface energy balance equipment and remote sensors. Very lucky to get to West Antarctica. This field program was many years in the planning, but we were even luckier still when we got to West Antarctica because we were able to sample one of the major melt events in the satellite record. And with our radiometric equipment and remote sensors, we were able to diagnose the mechanism for inducing surface melt in West Antarctica. So very successful. Many papers have come from AWARE. AWARE data have been used. This West Antarctic case study has been used to evaluate climate model performance. Very successful campaign, but then the next question is, where do we go from here? Is this it for this kind of science in the Antarctic? This is the kind of thing that comes along once in a generation. We kind of at a dead end. Where can we go from here? And so I didn't want to just stop doing this kind of work, so I decided that how do we figure out where to go forward? And so one way to go forward is to take a look around and recognize what other Antarctic programs are doing. So this slide is not an exhaustive survey by any means. It's just 3 of the programs I've followed with some interest over the years. Of course, there's Irina's program at Princess Elizabeth Station, where she's been gradually building up atmospheric science capability and is now looking at atmospheric rivers and their influence on surface mass balance. And then another interesting set of papers has come out from Dumont-Durville, where they've deployed a cloud radar, and that's garnered some interesting results on how katabatic winds influence the surface mass balance through sublimation of precipitation. An interesting result there. And then the British Antarctic Survey has been equipping their Twin Otter aircraft with cloud microphysical equipment, and they've made numerous flights over the Antarctic Peninsula, and there's some really good papers from Tom Lackland-Cope and his colleagues that have some insight into secondary ice processes in Antarctic clouds. So with these kind of these examples as inspiration, what I decided to do is to see if we could scale down the successful equipment from AWARE into a very small, portable, solar-powered and versatile little field package that could go anywhere. And so this is the first set of instruments that I was able to buy once we obtained some NSF funding for this. Basically a broadband radiometer stand, Kip and Zonin instruments, a Campbell Scientific eddy covariance system, and then one cloud remote sensor, a stellar net spectroradiometer covering both the visible and near-infrared wavelengths, and then an all-core system all-sky camera. And you can see in the green I've put the prices as of 3 years ago. This stuff is not very expensive, so you can just add these things to your package incrementally. This is just a few years ago. This kind of equipment would have cost 5 times as much, but the price points are coming down for some quite some powerful instruments you can buy. So we deployed this at Siple Dome for a month, and we were able to get now at Waste Divide with AWARE. We were on West Antarctica, but we were at the summit, so we were kind of removed from where the greatest climate concerns are, which are more toward the coast, near the vulnerable ice shelves and so forth. But at Siple Dome, we were able to get close to 2 of the glaciers that are of interest for climate change, the Cam and the McHale ice streams. So it was a relevant deployment in that sense. And then here, at the center and right here, just a couple of things, a couple of the fields we were able to measure. The surface albedo, This is just a time series of the surface albedo sorted on sky conditions from the all-sky images. And you can see under cloudy skies that broadband albedo is a little higher than under clear skies or broken skies, as you would expect. So that's something that is data that could be used to evaluate that component of a climate model on a daily basis. And then at the far right, we have a time series of the cloud conservative scattering optical depth and hourly averages from the spectroradiometer, retrieved from irradiance at about 1020 nanometers. So that's another thing that could be compared with climate model output in terms of cloud optical depth and liquid water content. So I think there's a lot of good, useful stuff in this data set. What I'll do now is just go through a couple case studies, which I think are quite interesting. And here in these case studies, I'm going to compare some of our observations with ERA 5, just as kind of a proxy for a climate model. I'm not a modeler myself, so I use ERA 5 because it's easy to download and look at it. But these comparisons are the same kind of thing you could do with any model. So the first case is a West Antarctic squall that happened over Christmas. Some fairly strong winds, not hurricane force by any means, but a squall that made us stay indoors for a couple days. And for a couple days, the winds were pretty high, and then it died down, and the winds, which were initially northerly during the squall, relaxed to become a little bit more westerly. And we see here that the ERA 5 wind speed and direction is pretty good. So somehow the ERA 5 is getting the surface the surface wind fields at least pretty good over Siple Dome during the squall. Looking at the radiative fluxes, I'll start on the bottom. We have all sky images every 5 minutes showing that this is mostly cloudy, occasionally broken cloud cover, but these radiative fluxes are consistent with fairly hefty optically thick clouds most of the time. The little arrow points to a little blip in the long wave fluxes, which is explained by the broken cloud cover. But as you can see, especially in the long wave fluxes on the right, this is optically thick cloud cover, bringing the net long wave flux to close to zero throughout most of this case study. And then if we look at the melt energy flux, the sum of both the turbulent and the radiative fluxes. We'll first look at the upper right, the turbulent fluxes. Again, the ERA 5 is not doing too badly compared with the observations. The one exception might be at the beginning of the squall, where ERA 5 was overestimating the turbulent flux, but it's overall qualitatively pretty good. Then if we look at if we compare the total melt energy flux to ERA 5, what it comes up with, most of the time it's okay. The ERA 5 is about 20 watts or so low compared to the observations. That could be something, some error in the cloud water content, or it could be the radiative transfer model. It's worth looking into. But on the final day, the ERA 5 just completely diverges from the observations, and then at the lower right we see exactly why. We look at the ERA 5's total ice and liquid water content, and on that last day the ERA 5's cloud microphysical scheme is just falling flat on its can. It's just failing to make clouds at all on a day where the observations clearly show that there's some optically thick cloud cover. So that's the kind of thing you could use this data for, to see if there's anything really going wrong in your model. But I'm going to talk now about a little more subtle and interesting case that has to do with Siple Dome being kind of on a plateau upon which clouds, mixed phase clouds from lower elevations will come up in the morning, and then they'll precipitate through the day and then become more liquid water clouds during the afternoon. And so we have a 3-day case here that starts out with a clear day. You can see that clearly in the short wave and the long wave radiation on that first day, and then 2 cloudy days in which these clouds advect up the dome. And if you notice the net long wave flux shown in black on the right panel, it tends to relax a little bit away from zero. The net flux is zero in the morning, and then it's relaxing by about 20 watts per square meter each day. And this is even clearer if you just evaluate the total radiative flux. Again, we see this long wave net just relaxing away from zero as the day progresses. And then finally, one thing to note on the lower right here, where we have the total melt energy flux and then the surface skin temperature, it's worth noting how closely the skin temperature tracks the melt energy flux. At the beginning of that time series, the skin temperature warms by several degrees just from solar heating, but then when the clouds come along, again, the skin temperature tracks what's now the cloud radiative flux from the long wave influence. So one thing we have is our little spectroradiometer, which is a cloud remote sensor. We had the same kind of measurement in AWARE. With AWARE, at waste divide, we had a micropulse LiDAR, which could tell us unambiguously whether a cloud was liquid water or ice water. And then with that, we were able to identify the types of spectral signatures you see in both cases. And they have 3 samples from AWARE on the left panel here. That red curve is a clear sky, but then the green curve is a liquid water cloud, and you can see that it has a different spectral signature in the near infrared 1.6 micron window. That's a contrast from the ice cloud. They have different slopes around 1600 nanometers, and so that can be used quantitatively to retrieve cloud properties. I'm currently working on that with one of Sam LeBlanc's algorithms. But here we can see it qualitatively just in a kind of a time series of these spectra. And on the right here, we have that first day, 11 January. The top curve is clear skies from the previous day, and then following the legend down, we start the morning with optically thick, essentially nearly all ice clouds. These are mixed phase clouds bearing precipitation. As the cloud precipitates throughout the day, the spectral signature tends to follow a liquid water cloud toward the afternoon. And we see the same thing on the next day. Again, in the morning, spectral signature in the 1.6 micron window, consistent with ice cloud or mixed phase cloud, and then becoming more liquid water cloud-like toward the afternoon. So that's what's actually happening. That's what we're observing. If we look at what ERA 5 is doing, it's doing absolutely nothing like that at all. So no, we don't expect any great things from ERA 5. It's basically, I think, it's just a diagnostic cloud scheme. But this is the kind of thing you could look at a much better cloud microphysical scheme and compare it to this kind of data and see if your model is getting something realistic for you. So to conclude here, with AWARE, a big field program, we needed C-17 flights to get to McMurdo Station. We needed an LC-130 to get to Waste Divide, and we were only allowed one LC-130 flight, had to take all 4 of us and all of our gear. So that was pretty massive, and it's kind of something that happens once in a generation. But with this new equipment, which you've seen the kind of preliminary package here, we can obviously add more instruments to it. This is all transportable in smaller aircraft that the U.S. Antarctic Program operates, such as the Basler or the Twin Otter. And so we can go a great many places in the Antarctic now with this kind of equipment. Our Siple dome data are already archived with the U.S. Antarctic Data Center. So feel free to look at it. It's pretty easy to use. I think it's documented pretty well. And we have a manuscript in review with Journal of Climate entitled The Siple Dome Challenge: Can Your Model Match a Unique West Antarctic Data Set? So that's my story for this afternoon. I'll take any questions.
Thanks very much. Any questions? Yes. Oh, sorry.
Thanks. It's really great work. It's actually a short question.
Sure.
So, is it yes or no, the answer to the title of your...
I couldn't hear...
what is the answer to the title of your paper?
That's up to you. That's up to... it's a challenge. Take your model and try to match this data. The manuscript's written to challenge people. And Siple Dome is tricky because it's, it has kind of a microclimate. It's a plateau, so you probably need a fairly high resolution model, but, the real thing is, does the cloud microphysics work? That's really the challenge I'm after here.
Because you showed, the ERA 5 is not really capturing it. But
no, I just put ERA 5 there just as an example of how to make these comparisons, but obviously, maybe somebody should try to improve ERA 5, but there are other things like RACMO or AMPS or things that probably might need more attention or might deserve more attention over the Antarctic. A question here?
Yes, I was Find it interesting the microwave spectra that you're showing and how you detect different kinds of clouds. But is there a way to make it more comparable to what models produce as information?
So that you think you're referring to the near-infrared irradiance spectra? Yeah. So yeah, the answer is yes. There are some algorithms that can take that spectral information, which I just discussed qualitatively, and turn it into cloud properties. There's a great paper by Sam LeBlanc at NASA Ames, and he's taken exactly this information, and he has some, he has like a 13-step or an 18-parameter algorithm, which will get cloud optical depth, thermodynamic phase, sometimes effective particle size, and we're working with that algorithm now. So that would be kind of the second paper based on this. And one can do similar things with the all-sky camera data, right? You know, their algorithms can turn that into cloud fraction. So there's a lot of things that can be done with this kind of data set. Yeah.
All right. Thanks, Dan.
Sure. Thanks, Rand.